Doppler effect in sound. You might have noticed that when an emergency vehicle passes by you, there is a change in the pitch of its siren. While the vehicle approaches, you hear a high-pitched sound. And when it recedes, you hear the sound at a lower pitch. The change in the pitch results from a change in the frequency. This phenomenon was first studied by an Austrian scientist, Christian Doppler. The apparent change in frequency of a wave due to the relative motion between the source and the observer is called Doppler effect. In this topic, we will understand the phenomenon of Doppler effect. The Doppler effect is observed in all types of waves, that is, electromagnetic waves as well as sound waves. Let us first study the Doppler effect observed in sound waves. We know that in the real world or three-dimensional space, the sound propagates in a medium in the form of spherical wave fronts with the source as the center. For the sake of ease in understanding, we will represent here the propagation of sound in two dimensions, in the form of circular wave fronts with the source as the center. Consider a stationary emergency vehicle blowing the siren. The emitted sound waves spread out in all directions. This gives rise to a concentric circular pattern of waves. Let us first understand certain terms related to waves on the basis of these wave fronts. Wavelength. The distance between any two successive wave fronts is the wavelength of the sound wave and is denoted by lambda. Frequency. The frequency Fs of the wave emitted by the source is the number of complete waves that pass a point each second. For correct measurement of this frequency, both the observer and the source should be at rest. Pitch. The frequency determines the pitch of the sound. The higher the frequency of sound waves, the higher is the pitch. The velocity of sound wave is expressed in terms of the wavelength and frequency as V equals Fs lambda. Having understood the essential terms, let us now study the Doppler effect. Stationary source and stationary observer. Initially, when the source and the observer are stationary, the wave fronts emitted by the source are concentric. The frequency measured by the observer, Fo, is the same as the emitted frequency, Fs. So, the Doppler effect is not observed in this condition. Next, suppose the source is moving. We can see that the wave pattern is distorted and is no longer concentric. The waves ahead of the source have been squashed, and those behind are spread apart. Why does it happen, though the source is still producing waves with the same velocity and frequency as when it was at rest? Let us understand this. After emitting a wave front, the source or the center of the circular wave fronts moves a little distance ahead before it emits the next wave front. Thus, as the source moves, the centers of the wave fronts move in the same direction as the source. This shortens the distance between the wave fronts ahead of the moving source. Therefore, the apparent wavelength decreases. Simultaneously, this movement of source also lengthens the distance between the wave fronts behind the moving source. So, the apparent wavelength increases. However, the velocity of sound V equals F times lambda is not affected by the movement of the source. So, the change in the wavelength in either region results in a change in the frequency. In the region ahead of the moving source, the frequency increases, while in the region behind the moving source, the frequency decreases. However, Doppler effect is also observed due to the motion of the observer, or both. We shall discuss different cases of Doppler effect in detail in our next topic. Summary. The apparent change in frequency of a wave due to the relative motion between the source and the observer is called Doppler effect. The Doppler effect is observed in all types of waves. When the source emitting sound moves in the region ahead of the source, the apparent wavelength decreases while frequency increases. When the source emitting sound moves in the region behind the source, the apparent wavelength increases while frequency decreases.